Started. Okay. So, hello everyone. This is part of a new series where I interview graduate students and ask them to talk about their research. And the idea of this series is to get the public to know what the frontiers of science are and try to advertise or promote the research of young scientists. Uh, th- Also, at the end, I will add a couple of fun questions. This is to make the interview a little bit more fun for the viewer and both us, so it's not such a stiff talk. Today, I have the pleasure of talking to J. Isaac Garcia from the University of Auburn, or Auburn University. He is working mainly on atomic structure, machine learning, spectroscopy, and I will let him talk about his research in more depth. Hi, Isaac.
Hey,
Joseph, perhaps to tell us first in layman's language what your research is about, and then I'll let you go full-on physicist afterwards. Yeah.
sure. Could I share my screen? I have a nice,
Of course, sure.
yeah, I have a nice
Have I
set
allowed?
of pictures here. So, okay, let me share this. And here is my presentation, this one. So, yeah, so what I do is, so what my research actually applies to is dielectronic recombination in low temperature plasmas. So there's a nice picture of this. This is a cartoon actually that my advisor made. The picture that we all have in our head of how electrons recapture into ions, that is just an atom with charge. It has lost some of its electrons, is basically where there's an electron floating around here, like in this cartoon, and then it spontaneously radiates some extra energy, some light, and then it falls into the nuclear potential. The atom is positively charged, the electron is negatively charged, so they attract each other, the electron falls in. This, however, is not what happens at very low temperatures. It does happen, but not quite as often as the more complicated process, which is what I'm modeling. So this is a single electron process. It's one step, one quantum transition. What I'm actually modeling here is dielectronic recombination. So here's a cartoon of that. So dielectronic recombination is essentially where you can think of it as the electron comes in, and instead of immediately radiating the photon, what happens is an interaction between the electrons that are already in the atom. So you can think of this as the electrons are in here, they're kind of forming like a net, and then that captures the electron that's coming in, kind of like impacting the net or the other electrons. And that impact causes an excitation within the atom. Then one of those or both of them has to radiate, relax, and then you complete the process of recombination. So this is a 2-electron process, and it involves 2 steps to quantum transitions. Okay, and there's a little bit. Here's where we get a little bit more detailed, but maybe we should stop there for now. Yeah. So I have more. So actually, you might wonder where would this apply? So this I think would also help lay people a little bit. So you can think of this as kind of like a downgraded particle accelerator, kind of like in the LHC. It's a storage ring. So these are our collaborators are doing this experiment. This is where we're getting our data to compare with. And basically, you can think of this as just a circle of ions. It's a charged ion beam that's going around in a circle. And merging with that beam is an electron beam, as you can see here in the smaller part right here. Basically, you match the velocities of both the beams. So this sets the electron temperature to be 0 in the center of mass frame. Then you detune the velocity to scan the energy space for resonances. And then recombined ions are filtered through a magnetic dipole chamber and counted to integrate the total DR rate. So basically, it's like you're trying to see, if you think of this as like the electron beam is kind of like a hose, you're changing the pressure on the hose, and then plotting as a function of the pressure, which is the energy, how many electrons are just getting captured by that beam of ions that is cycling around the circle.
All right. Yeah, that's quite interesting.
And so, so now I've given an example of the scenario, but I think for a layperson, they may still not know exactly where this is, like what is the most practical application of this. So this basically, once we get a resonance plot, but I can go here. Yeah, here we go. Okay. So once we get one of these resonance plots, these resonances have a specific pattern to them. You can see here's a plot that, so the gray is the experimental data and the solid line is the theoretical data. And basically every ion has a very particular pattern of peaks associated with it. So we can use this to identify what ions are in a plasma. And basically, this kind of procedure is meant to tell us what ions are in the plasma. What is the plasma made of? That's the fundamental question we're trying to answer.
So these are absorption and emission lines that you see from the plasma.
Right. That's right. Okay. So I think that's that's my explanation for the layperson.
Okay, so maybe you can go into a little bit more detail. I have one question first. Can you go back to the cartoon first, the one with the electron recombination process? So, to my understanding, when you do this kind of calculation in quantum mechanics, this is a multi-electron atom, correct?
That's right.
So are you using some kind of variational methods or are you using some perturbative methods or something else? Because in this case, I see that the capture seems to be a little bit different to the standard picture that we learn in the classroom. The standard picture we do is helium atoms with an additional interaction term. So how is that different from what we do typically in the classroom? Yeah. So.
Yeah, that's a good question. So here I can get into a little bit more detail. As you correctly pointed out, right? We think there's these, when you get to multi-electron systems, it can get very complicated. With a single electron system, you just have one ionization limit. But with multiple electron systems, you have multiple ionization limits. So this is where dielectronic recombination becomes a process that complicates things. Basically, if here you think you have a continuum state, then there's this transition to this other set of, this other, what would you call this? Series of spectral lines. And there has to be this energy match here for this transition to happen. So this sequence of spectral lines corresponds to a sequence with one excited electron. You can see here in the this would be a configuration where every other electron besides the one that has been captured is in the ground state. Versus this one where one of them has been excited to the 2p, for example. And so then there's this, in order for the process to be completed, one or both of the electrons has to relax. And this is another one just to point out that this could happen many ways, right? There could be multiple excitations here that happen. Okay, so you asked, how are we doing this to, like, how are we calculating these states, right?
Yes.
And how are we modeling the transitions? So what we do actually is non-perturbative, and that's not entirely true. But the way that we here, let me get past this slide here. So I'll just say what the procedure is generally. So we do what's called the central field approximation in ion systems. And so that you can think as your first approximation, you would say, okay, well, we can't solve this Hamiltonian exactly. We don't have the algebra to do it. What we can do instead is we can make this first approximation where we say that, well, at high energies, if you just imagine an electron excited very far out from the rest of the atom, you can say that all of these charges here are kind of like a point charge. And so that'll be your first approximation. So it's like a shielded nucleus. And then this gives us our first approximation, which is called the central field approximation, named so because, well, it would be centrally symmetric to first order. And so this gives you these eigenfunctions which are very similar to hydrogenic functions, except for this radial part. The radial part is what is being perturbed. And then now you do, this is the non-perturbative part. So instead of looking for a series expansion for the energies and the eigenfunctions, the actual stationary states of the system, what we do is we just take this Hamiltonian matrix, this representation of the energy operator, and we try and diagonalize that matrix. And so, well, okay, so this is where the real trick is, because this matrix in nature is infinite dimensional, and a computer cannot take an infinitely large matrix. So this brings me into the fundamental, how would I say? I would say it's the minimal assumption, the minimal criteria for being able to actually do this, which is that we can only solve systems whose Hamiltonian to a good approximation can be represented by a block diagonal matrix. So basically, you have these blocks of non-zero elements, but as long as you can say that these blocks are finitely large, then you can separate it up. And you can say, okay, well, everything off that block is zero. Now we can just get our computer to pick a particular block and just diagonalize that block. And so that has to be true. If that's not true, there isn't a computer in the world that could that could solve one of these systems. Actually filling these out and finding a good set of configurations to start with is the whole motivation of this research project. It's basically the hardest problem that we've had to solve. This is where I had to come up with a new algorithm to do this. The foundations of that come from Cohen's rules for configuration mixing. So there's 3 selection rules. These rules are always true for which configurations will transition into one another. So the first rule is basically that they have to have the same spatial symmetry, same parity. The second rule is that they can't be more than 2 electrons in different orbitals. And then the third rule is that at least one LS term must be in common. That's the orbital and spin total angular momentum quantum number. Now, that third one is a problem that I'll mention later, but basically this one is very hard to code up, and so we've kind of skipped it. But yeah, it requires more analytic development. I tried to actually solve this last summer, but I ran out of time, and so so I had to get back to other stuff. These are more important for the actual algorithm, which is what we call the propensity rules. And so basically, configurations are likely to mix when they are near an energy and within a complex, which is basically a complex is within each end shell, you have the same number of electrons, if that makes sense. Yeah. So here's where we get to, well, first of all, before I go to the next thing, do you have any questions so far?
Not really, but kind of with the Hamiltonian, there's one part I don't really understand. So you block diagonalize the entire Hamiltonian, and then you reduce them into sub-matrices. And
Right.
then so I kind of got a little bit lost what you do with these sub-matrices. So what do they represent, or what do they, yeah.
Ah, I see. Okay. So these, right. So this is what we're hoping for. So now I can say in more rigor exactly what is the minimal assumption here. So now that I've said what a complex of configurations is, and I'll say it again just in case. So it's basically a set of configurations such that within each end shell they have a common number of electrons populating each end shell. So the minimal assumption then is that those complexes are asymptotic to the blocks in the Hamiltonian. That is, that as you go up in energy, the blocks in the Hamiltonian will correspond exactly to the complexes.
I have one more question. But regarding the central field approximation. So from what I understand is you assume that the charge density is kind of a point charge. Is that approximation for the electrons on the outermost shell where the interaction occurs, or is it with the ones with the inner electrons as well?
The approximation is used for all electrons, and this is so it seems kind of bad, right?
I don't know. I don't know. That's why.
You would assume that it only works when you have an electron that's very far away from the rest of the system. This is it's surprising that this works as well as it does, actually. This is where, so I think I didn't actually answer the question that you asked before, so I'll answer that right now. You asked what do the blocks actually represent? So if we think we're high up in energy where one of the blocks actually corresponds to a complex, then I can say that those blocks represent transitions. They represent you can think of it as the first order transition rate from one configuration into another configuration within the complex. And generally you can think of all of the off-diagonal elements of the Hamiltonian that way. They represent a first order transition rate.
Okay, I see. All right, thank you. Yeah. So yeah, continue.
Okay, sure. All right, so so we have this block diagonal Hamiltonian, and we have the rough idea that as we go up in energy, we're hoping very much that those blocks will correspond exactly to the complexes. So with this in mind, we tried a whole bunch of different ways of trying to take shortcuts. Hopefully this would be a low-hanging fruit, but unfortunately it wasn't. This has been a problem in the field for more than 20 years for a reason. It's because actually this kind of problem isn't the kind of problem that a physicist would usually want to try to solve. But this is what seems to be working now. What we do is we organize the configurations, first of all, into a tree data structure, and that naturally arises as the most memory efficient way to loop through all possible configurations within a maximum end shell. Again, we have to work with the finite memory requirements of the computer. So you have to set a maximum end shell at each iteration of this algorithm. In order to do this, you have to actually transform from, so these values at each of these nodes on this tree, they don't actually correspond to the occupation at that node. What they correspond to is a sum of occupation numbers from that node to all nodes below. So if this is an ion with 4 electrons, then the root node is always going to have a value 4, because if you were to add up all the electrons from here below, it's always going to be 4 electrons in the whole ion. And then this is how you make it really easy to loop through all the possible values. You say, okay, well, I can imagine then promoting 2 electrons up from there has to be at least 2 electrons above the lowest energy orbital, because, well, only 2 electrons fit in the lowest energy orbital. So you can think of these as defining configuration prefixes. And these I have labeled here. So at this node, you have all configurations that start with the prefix 1s2. And so you can find the ground configuration right here at this leftmost node. And that is all configurations that start with the prefix 1s2, 2p2. Of course, that's the trivial case. At the opposite extreme, you can find very high energy configurations. So these are where there are no electrons in the lowest energy orbitals. So in this one, you would have all configurations that start with the prefix 1s0, where over here you would have very, very high energy configurations this with the prefix 1s0, 2s0. Okay, so now, the idea then is to move through this tree and truncate it such that it starts to iteratively converge on the eigenenergies on the spectrum that you're looking for. There's a problem here, which is that multiple configurations or multiple nodes on this configuration tree can correspond to the same complex. So for example, these that I've highlighted right here, they actually correspond to the same complex. And what we found just empirically is that if you remove configurations that are in the same complex, you can actually risk degrading the spectrum, where if you remove the entire complex, you can actually stand a chance at improving the spectrum. So it's a complicated problem, and if you try and do it at this level, you're actually not going to, you're going to end up with a very finicky algorithm. So what I had to do really, is I had to add another layer to the tree. And at this layer, at the upper layer, the levels of the tree now correspond not to orbitals, but now they correspond to end shells. And so those three nodes you see in red here actually correspond to this one node right here. And so if you were to just remove this one node from the tree, you'd be sure that you've removed an entire complex. And this is good. This is what we want. So this is, of course, this is where the name of the algorithm comes from, is the complex resolved ion spectroscopy tree algorithm. I call it CRISTAL. So, okay, so so to get into a little bit more detail about how this actually works. So like I said before, I call these nested sums. This value at a particular node is given by the sum of occupation numbers at that node and all subsequent nodes. And then it becomes really, you can set a maximum and a minimum for the children of that node. Okay, and so it's not too important exactly what these, the important part is just defining it this way makes it really easy to populate it with a for loop. So, and then another good orienting example here is that the immediate family of the root of any one of these trees is always going to look this way. Simply because there's only 2 electrons that can fit in the lowest energy shell. And so you'll always have the total number of electrons here in this root node, that number -2, that number -1, and the total number here. And these will be all of the nodes that are attached to the root node. And so here is probably the most important slide that I wanted to get to. These are the guiding principles of the algorithm. And so basically, it's that the safest branches to remove are going to be those that are highest in energy. This we can say, okay, these probably are very close to being block diagonal elements, and they're probably not mixing with any of the other ones. So you start with the prefix 1s0. And the remaining configuration sequence should be complete within what I call a quasi-Fermi surface. So if you were to think of a surface in quantum number space where basically all the configurations below this surface are important for the calculation, and all of them above you can throw out. So this makes it like a staircase pattern, where if a branch must be kept, you move down the branch. If a branch is successfully moved, you choose the sibling with the highest value. And then all remaining branches should extend to the maximum end shell that you gave to the structure code, simply because short branches can cause a navigation error. So that also tells you where the algorithm terminates, is once the staircase reaches Nmax. And here's a little diagram of how that all works. So this is if the spectrum degraded when you remove this node, then you get a little bit more specific and move down the tree. And then, of course, this terminates once you get to the maximum end shell. And then if you removed a node successfully, then the next node that you should choose would be the sibling node with the highest value. And then, of course, that terminates once you're at the maximum end shell. Okay. And then one point of complication is just that sometimes in this tree you'll end up with chains where basically the parent node has only one child, and then that child has only one child, and so on. And so I'm not going to go into too many details about how how you account for this, but basically I'll just say that you don't want to leave, like I said before, you don't want to leave a short branch. So either you skip to the bottom of the chain or you truncate it right at the top. And this is just me showing that those cases, they're all either going to feed into each other or they're going to terminate somehow. So this is just a connected network of, of cases to show that it'll eventually terminate. Okay, and here's the preliminary results that I got. The fully automated version of this is I'm still debugging it, but I implemented this algorithm just using user input, and yeah, it got pretty good. We beat our goal was an average difference of 0.1 EV. We got to an average difference of I think it was like 0.03 EV. If you yeah. So we're doing pretty good, and we expect that the fully automated version. Actually, I did a run with the fully automated version, and it did beat me by a little bit. So I haven't run it very long. So but I'm pretty confident that if I kept it running for a long time, it would do a lot better. Yeah.
Sorry, one question. By average difference,
Sure.
do you mean the difference between the So I see it says NIST energy. Does that mean the
That's right.
experimental value, correct?
Yeah.
Or yeah,
So
okay.
NIST energies, right now we're using the energies recorded in the National Institute of Standards and Technology. So you can look these up online.
I see. I see.
But we could very easily just replace those with, if we needed we could replace them with the measurements from our storage ring
I
collaborators.
see. I see.
Yeah. Okay. I think I already talked about this. Yes. So if you want to know, yeah, so there's some things that I didn't mention here. These are the future goals. Basically, as I mentioned before, we're hoping that that the Hamiltonian actually is within the memory limits of the computer. Right now, the algorithm is blind. Basically, it's just feeding in configurations to the structure code and hoping that this minimal assumption is actually true. So what we want to do is basically the structure code. By the way, that I keep mentioning this structure code. It's a spectroscopy code called autostructure. It's a little bit older, but it's easy to use. It is a serial code, so that is one limit. I think, though, that there might be a parallelized version. I'll have to check on that. But basically, what we're hoping is that, or I should say instead, we need to tweak this code so that it will actually output the elements of the Hamiltonian, not exactly the elements, but to output the intercomplex energy variance, basically to find the transition rates within between complexes, not within a complex, but from one complex to another. And we need to show that that transition rate will go to zero. that would tell us that this is actually behaving the way we need it to in order for the algorithm to actually converge. So that's one very important thing. Another thing that I was trying to do, I mentioned this before, was we want to also include Cohen's third selection rule, which is that at least one Ellis term must be in common between two configurations that transition into one another. But this would, again, I mentioned this before, but it would require a general formula for angular momentum coupling coefficients. So I did manage to derive a formula in general for the case of two quanta, and this is the formula. And I have checked this with tabulated values, it works. But I found last summer that if you try to generalize this to more than two, the formula just blows up way more than what I have here. So, I'm trying to, there's a particular condition that I have a criterion to show that this operator actually generates the state that we want. I need some more time with this. Hopefully I can come back to this before I have to graduate, but if not, maybe I'll do it for a postdoc. So yeah, so this is one. The other one that we would like to do, and this one actually I will come back to before I graduate, which is that there's another source of error in the DR rate. So if you think getting the spectra right corresponds to putting those peaks in the graph that I showed before in the right place, getting the transition rate right corresponds to getting the heights of those peaks correct. And this is where there is another source of error, because actually most of the atomic spectra codes, they use what's called Fermi's golden rule, which is known to be a first order approximation to the transition rate. And so, well, the exact transition rate, actually, this has been solved by Freeman Dyson. I wish I could have met him before he passed, but well, anyway, yeah, he came up with this amazing solution that is far more general even than quantum mechanics. But this is the Dyson series, which is the most complicated equation I've ever written down. It's a summation of products of integrals of matrices. Yeah, this actually would give you the exact solution, perturbatively, but we hope to use this to set an upper bound on the error from a first order approximation. And this would basically give us a rigorous rule to say, where is a first order approximation actually good and where is it not good? I feel like if you're using approximations, you should at least know that. So, okay. I think that's everything that I have here. This is...
I do have two questions regarding your
sure.
very last slide. It's really interesting, actually. Could you go back one slide?
Sure.
For implementing the Cohen's third selection, it's not a simple matter of calculating the Clebsch-Gordon coefficients, right? It's much more complicated, right? Can you the slide before, the one with the future work, I think. It's the very last slide you showed, I think, before you showed the reference. This is
This
the
one here?
Yeah. So you said you won't work on the second point for a very long time because it's very hard. Like, can you kind of explain what you have to do? Because to my naive understanding, I know that to calculate the angular momentum coupling coefficient is just not just, but like calculating the Clebsch-Gordon coefficients is already in general a pain. So
yeah.
What makes this part a little bit much more difficult in some sense?
Yeah. Let me think about that for just a second. Okay, so what makes it more difficult is that, well, there's a certain approach that, no, that's a tangent. I'll have to skip that. So instead, I'll say there's a couple of things that make it more difficult. The first thing that makes it difficult is you have to make sure that the state you end up with is a physically allowed state.
Ah,
Because if you just naively look for the Clebsch-Gordon coefficients, you can find some where the state that it actually gives you is a symmetric state, which is only true for bosonic systems. Where for electrons, of course, you want fermionic systems. So you want a fermionic state. So that's one source of complication. That's probably the fundamental issue is you need to find and I think this helps me connect it back to what your original question was, because you said it's not just finding the angular momentum coupling coefficients. You have to connect it back to Cohen's third rule, which is finding the actual LS terms. And so to find the LS term for a given, it's finding the LS terms that that a given configuration can produce. Basically, you can think of it that one LS term actually, and I'm going to tell you a dirty secret about atomic structure, which is that actually an LS term isn't specific enough to tell you what state it is, because there's multiple ways you can end up with the same LS term. So you can think that there's some equivalence class there. And an equivalence class, or I should say, a configuration is an equivalence class of LS terms, and an LS term is an equivalence class of actual states. So yeah, it's like nested equivalence classes.
That's extremely complicated.
Yeah, but yeah, so there's a couple layers of complication there. One nice thing that this gives you is that this formula here gives you is that if you actually work it out, which states will be allowed physically, which ones will be antisymmetric. It's the cases where the sum of total L and total S is, I want to say it's an even number.
Even number, okay.
I think so.
Okay.
Or maybe it's that it's an odd number. I can't remember. It's one of those.
Either one of them.
It has a particular parity. This is where it gets more complicated in the case of multiple electrons. Actually, that rule only works when you have two. If you have more than two, then you can't use a very simple rule like that. You have to go through the total J's and then work backwards to get your total L and total S. And then that will tell you what the LS term is, and then you can say what LS terms the configuration generates. Yeah.
Trying to derive this analytically would be extremely troublesome. It's something that I would never want to do.
Yeah, this is another reason why it hasn't. I feel like just people don't want to work on this problem is because it's no longer low hanging fruit. It's very high hanging fruit.
Yeah.
But yeah, I got very close, I think, to solving this. The problem was that. Let me see if I can actually find. Well, maybe I'll save it. I'll say that there's a nice commutation relation that you can use. Actually, I think I had it in my. Yeah, I think I had it in my. Yes, I have it right here, I think. If I present this one, so let me. It's just that there's this thing in the way. What if I do that? Okay, and then if I do slideshow.
Ah, there we go.
Nope. What happened? This one. Oh, right. This is the wrong slide. I'm sorry.
All right,
Okay. Um,
take
how
your
about
time.
I'll do this one. Nope. It's the second committee meeting. There we go. Okay. And
So,
now if I just do this slide,
uh,
go to slideshow and immigrant slide. Okay, let me see if I have it here. This one. Okay. So yes. Okay. So these are the two relations that seem to generalize to tell you what. Yeah. These will tell you what. Basically, what I did was I. You can think of it almost as a creation operator. That's what this J here is. The problem is that so if you were to just use what we do in quantum mechanics, in introductory quantum mechanics, to find the Clebsch-Gordon coefficients, what we typically do is that you use what's called a ladder operator, right? You might remember this. And
yeah.
so, yeah, so the ladder operator will loop through the possible allowed states, but then you get all of the ones that are allowed for that total J. And then in order to get the next ones, you have to find some state that is simple and is orthogonal to all of the previous ones. And well, if you had a computer do this, it'd be fine, even for multi-electron systems. But if you want to do this analytically, that procedure of doing that and then finding the one that's orthogonal and then doing it again and then so on, that's just not
It's a
practical for a
pain.
human
Yeah.
to do. So instead, what I did was that I constructed this operator, this script J. And the script J, what it's meant to do is to take the simplest state you can imagine would be the state where all of the electrons are aligned with the vertical axis. It's not a physical state, but all of them are aligned with the vertical axis. And the state is completely factorizable. So again, that's not a physical state, but basically what I did was I said, okay, well, you can use that as an input and then imagine some operator that takes you from that state to a set of states which are physical. And so this is basically what the idea was to find this operator. And then these are the commutation relations that define the properties of that operator. And these commutation relations are very generalizable, but I ran out of time to solve this. And I found one issue with this, which is that actually this doesn't determine it well enough. You have to impose another condition, which is permutation symmetry, because you have identical particles. And once you do that, then you'll get something that is usable. But I haven't completely worked out all those details yet. So hopefully I
Well,
get a chance to come back to this and I can work it out and
I
publish.
mean, the fact that you were able to construct an operator to me is quite impressive. I mean, you can even show that it satisfies an algebra, which is quite nice. I
I
don't know.
appreciate that.
It's quite interesting. I don't know. If you don't mind me asking, how did you guys come up with this operator? It seems, I mean, if you ask me
Um,
to come up with something like this, I would be able to figure it out, right?
yeah, I don't know. I was sitting there trying to work on it one day, and I was like, okay, well, if I was like, okay, well, obviously the computer could recursively do something like this, but if I want to proceed analytically and get some kind of a rule that tells me what LS terms are actually allowed given a configuration, then doing it recursively is just never going to be feasible. So I figured that I needed some kind of operator that would be that would help me. If I could generalize this to the level of some operator, then I could say, okay, what are the symmetry properties of this operator? And then my rule would come out of just the symmetry properties of one of these operators.
Yeah, I mean, that's really interesting. Like, I don't know. I thinking people who do atomic physics, I wouldn't be able to come up with this if you gave me like a year. So like come up with this kind of operator and show that it satisfies this kind of algebra and it's yeah, I don't know. It's quite an interesting
Yeah,
piece of work. Yeah.
I don't know. I guess it's just when I get on one of these problems, I don't really think about anything else. I get it kind of like takes up my whole neural network, and yeah.
I do have one more question. So I
Sure.
remember you showed me, we talked about this before the interview started. I asked previously how does I remember you showed me somewhere that this has to do with astrophysics, and I'm just
Yeah.
interested, like, could you elaborate on that here maybe a little bit more? Yeah.
Oh, right. Yeah, yeah. So let's see. It does have to do with astrophysics.
I remember it's something to do with interstellar medium or something like that, but I can't remember the exact details. So it was quite or some kind of
Yeah.
plasma in the yeah, I can't remember, but it's quite interesting because the p colleagues at my university, I'm in the astrophysics group, so I would just like to know as well. Yeah.
Sure. Yeah. So I think this is the slide that I skipped actually.
Mhm.
So if you look at the discrepancies,
Mhm.
so the problem that I'm trying to solve really applies to the case of a low temperature plasma, because
Mhm.
at high temperature, you could think all of the states are already very, very close to being stationary states.
Mhm.
Whereas once you get down below about, and I say low temperature here,
Mhm.
it's just to distinguish it from fusion
Yeah.
plasmas. So
Yeah.
actually,
Mhm.
this is I think it's about 100,000 Kelvin still,
Mhm.
so still pretty high temperature, but by Earth standards. But yeah, so in this yellow region that you see right here, this is where the problem starts to
Mhm.
arise.
Mhm.
So to get back to where this applies to plasmas, okay, so you could actually think, let's imagine not a beam, but some thermal distribution of ions
Mhm.
in a bath of electrons. So this scenario is like a plasma. Then you could convolve this with a Maxwellian distribution, and then produce what's called a Maxwellian rate coefficient.
Mhm.
And then here's where you see really what would be the penalty of missing one of these resonances here.
Mhm.
If you imagine these, I think the dotted curve is one of the experimental ones. And then this curve right here is the calculated rate having missed this very large resonance right here, which is perfectly possible to happen. Then you'd get this huge discrepancy in the rate coefficient. That's no good. So coming to a more tangible example, we'll say let's say you have a planetary nebula, and let's say you just want to calculate the charge state abundance of carbon. So how much carbon plus is there versus how much carbon 2 plus is there in this planetary nebula. And for a layperson watching this, I would say that a planetary nebula is just it's like an exploding star, like a late stage but main sequence star like the sun. What happens when the sun is starting to burn out? Well, it starts making this planetary nebula where the outer layers of the sun are getting blown off, and you just have this central star in the middle. Okay, so this is made by this code called Cloudy, which models photoionization in plasmas. And it uses tabulated DR rates in low temperature environments. So you can say, all right, well, I'm showing this graph right here. This is plotted, the x-axis corresponds to the distance from the central star, the distance from the surface of the central star. And then on the vertical is plotted the fractional abundance. And so if you use the current theoretical calculations without the CRISTAL algorithm that I've come up with, you get these solid curves here, which actually have a crossing point between the two fractional abundances. But if you replace that data with experimentally measured data, you get these curves here, which they never cross. So this is another place where the current models are no good. But yeah, so to answer your question specifically, this applies in astrophysics to cases like planetary nebula, also to one of the things we're looking at is like later stage neutron star mergers, and those would be really interesting to look at. Yeah.
Yeah, I see. This is really interesting because some of my colleagues work on something called Bowen lines, which are forbidden lines of oxygen-3 and nitrogen-3. And what they do is
Okay.
instead of calculating all the, I think one of the pains is calculating all the possible transitions from oxygen, like co
Yeah.
declining. That's a real pain. So what they do is they pick, because if you calculate all of them, it would take forever. So what they do
Mhm.
is they pick the most probable ones using the Einstein AB coefficients. I think it's,
Right.
yeah,
Yeah.
very interesting. So yeah, I really enjoyed your talk, man. Like everything is like, for example, I really liked the mathematical parts because to me that's a little bit more comprehensible. But the algorithms is also quite interesting. The way that you kind of implement these selection rules. I imagine the last one, was it Cohen's? The one where you have to
Mhm.
code the angular moment, the coupled angle must be quite difficult to implement at the end, right? Or
Yeah. Yeah. This is why we're just
you want?
skipping it for now because it's
Yeah, yeah.
because
I mean.
I can't currently think of a way to code that in. Yeah.
I mean, you only have a finite time for your PhD, so
Right. Yeah.
so yeah, that's understandable. So
But
yeah.
I'm surprised at how well it's working so far.
Mhm,
Actually, if I come back to this slide that I have
mhm.
here towards the end, you can see that, oh, not that one. I think it didn't. Here we go. Current slide.
Mhm.
Okay, yeah. So if you look at the number of steps here, I think I forgot to say what this red line represents. This red
Mhm.
line represents just doing the recommended configuration sequence and settings in the atomic structure code auto structure.
Mhm.
And the spectrum you would, the accuracy you would, I should say the average difference with the NIST energies you would get for these particular levels right here.
Mhm.
They're listed by their configuration and
Mhm.
the J and so on. But you can see that just after 4 iterations, it already beats that one.
Yeah, that's
So even, I mean, I'm pretty excited about that. It would it would only make it run faster if we could include the third selection rule. But yeah, so far one of my collaborators was saying that we were getting within because they were looking at there's another guy in my group. His name is Clayton Chillen. He's a I want to say he's a second year grad student. And he just showed that if you're looking for what are called satellite lines, and this is where if you see one of those spectral lines, I don't have a picture of these satellite lines, but if you see one of these spectral lines right here, a satellite line is where if I was to zoom in on this, you would see peaks that are right next to the primary peak and smaller in rate coefficient. He showed that those satellite lines are accurate to within 0.01 angstroms with the current spectra with the current spectra we're producing with CRISTAL. So I'm really happy about that.
I have one naive question. So I see
Sure.
that the peak, the plot that you showed, it seems to be declining with peak. Is that a general trend? Because I see in the middle, it seems to be decreasing, and then there's a abrupt increase, and then you decrease at the end. So after, let's say n equals in on the plot, just not here on the plot just now where you showed the number of steps, where you compare the out of box with the,
Ah,
yeah.
yeah, that's something that
So
I forgot to mention. This is actually a very interesting. I'm glad you asked.
uh,
This is actually a very interesting thing that happened. So It turns out that as this algorithm is going, at the second step, it removes the prefix 1s1 from the configuration tree. So this is all configurations that start with 1s1. And if you were just thinking naively, you would think that those are too highly energetic to mix with the other ones. But it turns out that this causes a big degradation in the structure. So some of these configurations with the prefix 1s1 are actually important for the getting the spectrum to below the average difference that we wanted to get it to. Actually, we found that it turns out that if you're just minimizing, and this isn't for these energies, but for if you were minimizing instead of these levels that we picked are for the configurations nearest to the ionization threshold. Instead, you could imagine optimizing for the levels nearer to ground. So that would be the first couple of configurations nearest to ground. And in that case, it turns out that it still needs one complex from the 1s1 prefix, and that complex is basically where there are all three of the electrons that are above the ground orbital are at the second orbital, if that makes sense. So, or at the second end shell, I should say. Yeah. And then the rest of them are just double excitations. And just to reiterate, that optimizes the first two configurations nearest to the ground. It doesn't seem to be the case, and these are our most recent results that I don't have on here. It doesn't seem to be the case that that applies to the configurations nearest to the ionization threshold. You actually need even more of the 1s1 prefix configurations. And so anyway, thank you for asking. This was a result that we got that was very surprising, even to some of my advisors, older collaborators that are more experienced with configuration interaction. They didn't expect this result.
Yeah, I found it interesting because I noticed you showed, well, there's the one big plot and the four small ones. I always noticed that there was a large spike at n equals 2, and I was wondering what was causing that. And it seems to be, afterwards, it seems there's a general decrease in
Right.
difference in energy, but I see that there's a large spike at 2. So that
Yeah.
was interesting to me. But yeah, but it's really interesting. I think this result. Yeah.
To answer your question more directly, it's common that there will be spikes in the average difference, and this is actually how a decision tree typically works. So to speak in the language of machine learning, there's a cost function that we're using, and here the cost function is the average difference with the NIST energies. And a decision tree algorithm is not quite as fancy as a neural network. What it's basically doing is just a bunch of educated guessing and checking. And so every time it makes a wrong guess, that's where you'll find a spike. And so you can imagine that as this is going through pruning the branches of the tree, every so often it'll make a wrong guess. And that's what the spikes correspond to. So at this second stage, yeah, this spike is the first wrong guess that it made. The rest of them looks like it did a good job.
I see.
Yeah.
That's really interesting. Can I ask how many steps at maximum have you run this, or does it take a lot of power to
That's a
run
good
one
question.
step?
Since we've been testing this on smaller atomic systems, the calculations haven't taken too long. And so we've run it up to an Nmax so far of, it's still embarrassingly small. It's an Nmax of up to 11. Okay. So we hope to do this for larger Nmaxes. The problem is that right now we're trying to, as I said before, we're still in the debugging stage. So part of the issue with debugging is that you want your results as quickly as possible so you can fix any problems that arise. So this is why we're testing this on systems with a small number of electrons. As you can think, as the number of electrons in the ion increases, well, the number of integrals that the actual structure code has to compute also increases. And so you run into memory limits much faster. You also have calculations that will take much longer. So you can think, I think we did one at an Nmax of 7, I want to say, and with this was an 8 electron system with only 321 configurations. I say only, that's a large number, but we're looking at sequences eventually going above a couple thousand. But anyway, with only 321 configurations, the calculation took, I think, 8 hours to run. And so this is not optimal if you want to debug. Yeah, so you asked how many steps does this usually take? I think with that case, it takes around, this is pretty well representative. It takes around like
Five, 4 or 5 steps.
5 up to 10 maybe.
Uh-huh.
The thing is that it'll keep counting steps, but what we seem to find is that it gets to that branch with triple excitations, and then it ends up looking for just some finite set of triple excitations, and then the rest are all double excitations. And so, but then it'll keep running on just the double excitations, not truncating anything. So you can think that once it's gotten that finite set of triple excitations, that's where the algorithms really converged. And that tends to converge around, I would say, like 5 to 10 steps. That's what we've seen so far.
So I have one final question before let's get to the fun question. So I can see in the plot below where you have 4 different plots, like 4 different cases.
right.
The time, let's call it the convergence rate where the algorithm can meet the out of the box. Is that different for different electronic, well, not really electronic configuration, but different, I can see different J numbers here.
Yeah, these are
So
different states. Yeah.
yeah. So different states, does the algorithm work less well with some particular states or some other particular states? Does it converge less quickly or
Yeah.
more quickly?
Yeah, that's a good point. Actually, that's true. Some of the states just happen to be very hard to do.
Mhm.
I'm not sure why that's the case. I wonder if it's because I thought before that it was because we're using a non-relativistic Hamiltonian,
Mhm.
but what we have been seeing is that as we include the Bright-Pauli perturbations that make it semi-relativistic, there isn't that much of an improvement. However, we haven't fully solved that case yet, because what we really did was we took the answer that CRISTAL gave in the non-relativistic case,
Mhm.
and then we just took that configuration sequence and turned on the relativistic perturbations. Whereas what you would want to do more generally is to turn on the relativistic perturbations and then have CRISTAL run on that Hamiltonian. And so I'm still not exactly sure what the answer there is.
I see.
But yes, it is true that some states just seem to be harder to get the actual spectral line right than others.
I see. Yeah, I just found it, yeah, it's quite intriguing because it seems that some converge very, very quickly and some
Yeah,
don't. Some converge quite slowly. So yeah.
yeah,
Yeah, but yeah, I guess could it just be there's something, no, I don't know. Including the relativistic case seems to not have an improvement. I'm not sure. I mean, this is not my area. Me not being sure is quite normal, but it's quite an interesting phenomenon you can see. Yeah.
yeah. Yeah, I'm not really sure either.
Yeah.
Um,
So
uh,
yeah.
yeah, we'll see.
But it's already quite a good result, right?
Yeah.
So I guess I'll go to the fun questions now. So
Okay.
maybe the first one I want to ask you is okay, in my opinion, I feel like physics classes are kind of afraid to put math into their classrooms, right? So maybe I think
on
we've
what?
talked about this before on
Yeah.
through text, right? What kind of math classes? Maybe let's choose top 5 to 3. You can also ask me the same question. It's fine. So, what do you
Okay.
think all physics majors should take?
Um,
Yeah.
I'll answer. So I'll first I'll list the ones that aren't that probably wouldn't typically be taken by a physics major. So I
Yeah.
mean, physics majors would typically take like differential equations courses
Yes.
and yeah. Actually, I think that physics majors should take courses, and I think this should be maybe this will be a little maybe this will be a little bit of a hot take, but I
Yeah, it's
think
all right.
that
I mean, I say
yeah,
things that are a bit of a hot take as well, so it's all right.
yeah.
I don't mind
I,
sharing my opinions afterwards. So yeah, go ahead.
I think that definitely we should include more Lie groups stuff.
I agree. I
Like
agree. Don't worry. I
yeah,
agree. Yeah.
yeah. I think it just it shows up everywhere, and
Hmm.
it formalizes a lot of it. Also, it makes a lot of uh, it brings a lot of concepts that we use all the time together in a nice formalism. That one of the issues with it though is that this is a little bit of a criticism of the way that it's presented in mathematics. Is that it isn't well, that's a matter of finding a good textbook that is readable for physicists. The textbook that I used when I took my Lie groups course around this time last year was it was I can't remember the guy's first name, but his last name is Bump,
Oh,
and it's very fitting because when you're reading that book, you feel like you're getting a bump in the head.
I see.
uh, but yeah, it's that book had no introduction. It just starts out with talking about I can't remember what the first sentence of the book was like. There is up to constant multiple a finite Borel algebra that blah 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 blah.
Yeah. Yeah. Yeah.
Yeah.
I mean, yeah. I mean, I kind of agree with you because a lot of my friends do work in uh quantum physics and quantum field theory, and I'm surprised that they don't actually learn group theory and even not even Lie groups, just group theory in
Yeah.
their undergraduate degree. Um, I don't know if it's too much to ask because you do learn a lot as a physics major. You're just trying to get a sense of everything. But I
Yeah.
feel that in quantum mechanics, at least when I was doing it from their perspective, I found it tremendously difficult to understand. And then when I learned group theory, I found that a lot of these things are generalized to one kind of group. Like, some
Right.
of them, like the rotations
Yeah.
are SO3, blah blah blah. I don't know, but I think I was more exposed to group theory when I started. Well, I just took a class for fun when I was in undergrad. I took a solid state physics class, and they
Okay.
talked about the crystals, and the crystals
Yeah.
they generate rotation groups, and I thought that was quite interesting. So I just started to seriously learn group theory then. Is there any
Yeah.
other class that you would recommend? Like, I do
Um,
have one in mind. So, uh,
let's see.
yeah.
Another course. Actually, I really liked taking information theory while I was here.
Oh,
Yeah,
interesting.
this surprisingly helps a lot with understanding statistical mechanics
Yes,
because
yes.
yeah, I have always struggled with statistical mechanics because I always got the sense that it's just well I should say it this way. I get the sense that statistical mechanics was kind of the old theory of everything
Yeah.
before we had modern physics, right? And so in this vein, a lot of physicists don't really take it as seriously as they should, and I think that reflects in the pedagogy is that it's not. I don't feel like it's as fleshed. Like I've never until I took StatMech 2 at the graduate level, I had never encountered the Boltzmann equation,
Yeah.
which I thought was really interesting. Anyway, I would say that if you really want to understand statistical mechanics, which you should if you're going to be a theoretician, it's very helpful to take information theory.
Just saying, when you said I really struggle with statistical mechanics, you're not the only one.
Yeah.
I don't think I've met a single physics major that's hasn't struggled with statistical mechanics. Originally, when I was learning it, I thought the most difficult thing about it was I felt like you're just doing very complicated integrals all the time. It's like you're just integrating over the Fermi-Dirac distribution or the Bose-Einstein one. And I
Right.
didn't really understand the point of it until I started learning, not really information theory, but more like statistics, regular old statistics. And I kind of get it. It's like, okay, I get the idea behind it. Perhaps one thing would like people to actually learn more in undergraduate is probably complex analysis. I don't know.
Mhm.
I find that quite
Yeah.
useful when doing calculations in E&M, and even when doing
Mhm.
calculations involving integrals that are difficult to do. Some complex analysis would be very, very useful. I don't know, but they don't really
Yeah.
do that in undergrad.
Yeah, that was one of the ones that I didn't mention because, at least at the institutions that I attended, when we took our mathematical physics courses, they made it a point to spend some time on complex analysis. But
Mhm.
that just might be my personal experience with that.
I mean, for me, they did mention it very briefly, but I didn't, at least in my mathematical physics courses, I didn't really learn too much. Well, I guess I could say the most I learned out of my mathematical physics courses were partial differential equations. Like
Oh
those
yeah,
were really hit hard on those courses. But the other techniques were kind of just here's a little bit of everything and then just go on.
I
Yeah.
see. Yeah, yeah, I agree.
Yeah. Yeah.
Yeah, complex analysis would be really good. One topic that I wish we would, well, this is
Another hot
uh,
take.
not, I wouldn't say exactly a hot take, but I'll just say it and then we'll evaluate it. But
Yeah.
basically, I think that in the study of partial differential equations,
Uh-huh.
we would emphasize more the method of characteristics
Yeah. Yeah. Yeah.
because it's just like, yes, doing separation of variables will give you a nice answer that converges. You can skip a lot of steps and you can get a
Hmm.
solution and sum over whatever.
Hmm.
But I feel like that doesn't really give you the feel of what you're doing like
Hmm.
geometrically.
Hmm. Hmm.
This is what I really liked about the method of characteristics.
Hmm.
Also, something that I found, so some of what's written up here was actually me trying to do something like the method of characteristics to solve the Dirac equation.
Okay.
Yeah, this brings me to something else that I wanted to bring up. So this is going to go in my dissertation.
Uh-huh.
So the Dyson series that I showed you in my presentation
Yes.
is a Dyson series for non-relativistic quantum mechanics.
Uh-huh. Uh-huh.
And I always had in the back of my head that there should be something like that for the relativistic case,
Uh-huh.
but I never quite knew what that was. And a couple of months ago, I just decided, okay, well, what the hell? Let me give this a shot. And so I managed to derive the solution to the coupled Dirac equation,
Hmm.
and that does get you a Dyson series that is equivalent to the Feynman path integral.
Really?
Yeah.
That's really interesting.
And in order to derive that, what I needed was an operator solution to the uncoupled to the free Dirac equation.
Hmm.
And so actually, I it was challenging to derive this operator, but it was easy enough that I was like I could do it within like a couple days. So I was like, okay, somebody else must have thought of this. So I looked it up, and actually, the mathematicians have generalized it to some kind of case with I can't remember, like some multi-dimensional Dirac equation with
Yeah.
like yeah. But yeah, you end up getting these this it's a pair of Bessel functions that are summed together,
Hmm.
and one of them has like let me see it. Yeah, so on one of them is the identity operator, and on the other one, on the other Bessel function is like a factor of the 4 position and the, what do I call it? It's like the relativistic inner product of the four position and the gamma matrices, the Dirac gamma matrices.
Uh, wait, just wait, sorry, give me a second. The four
Yeah, sure.
position inner product, and then with the gap. Okay, yeah, okay, I get it. Okay.
Yeah. So yeah, what was I bringing this? Oh, right. So in the same vein, yeah. So it was actually the method of characteristics that made me think of that kind of a solution
Mhm.
because I was thinking, well, what would the characteristics of the Dirac equation be? Well, they would be elements of the Clifford algebra. And
Yes.
actually, this is what the operator solution is. It's an element of the Clifford algebra.
I'm I'm surprised you didn't offer something more like I wouldn't say that novel's not the right something more maybe I guess sophisticated like a Green's function. That's it. But I don't know. Is it
Yeah.
can you actually construct a Green's function? I'm sure you can. Right?
Hmm.
I don't know.
Possibly.
Yeah. In our differential equation class, we tried every single technique, and then they always say the first. They actually, what's nice about our differential equations class, they told us when exactly, you cannot use separation of variables, which I think is quite nice because a lot of people just blindly apply it without thinking whether you can use it or not. Yeah,
Ah,
that's
okay.
quite interesting. Yeah. So maybe let me move on to another question that I think is quite fun.
Sure.
So the other one is maybe recommend maybe 3 to 5 or maybe I don't know if five is too many. Some academic textbooks that you personally like that you
Okay.
maybe not live by, but that you use sometimes in your research and sometimes you frequently go back to.
Yeah. Yeah, this is a good question. I was talking about Lee Group's textbook. I would say if you're a mathematician, if you're a research mathematician, you would
Mhm.
very much like the one that I didn't like, which was Bump.
Yeah,
I really like Kirillov. That's the one
sure.
that I'm currently looking at to
Mhm,
relearn everything that, yeah. Anyway,
mhm,
a physics book that I really like, actually it's a classic. It's Wigner's book on group theory and
mhm.
atomic structure. Yeah.
I've seen that, but I've seen that in the bookstore, but I've never actually picked it up to read it because I don't know. Yeah. Is it like what do you like about that particular book? Like, is
It's
it?
a very accessible introduction to group theory for physicists.
I see.
That's it. Yeah.
It's really great.
Also, it relates it to very specific applications.
Mhm.
And it's the only textbook that I've ever found that addresses second order degenerate perturbation theory, second order degenerate time dependent perturbation theory.
Wow. Okay.
Yeah. So I haven't, or was it just second? No. I'm sorry. It's just second order degenerate
Different
perturbation theory.
perturbation. It's
Yeah.
not common, and even then, it's not common. I remember seeing it for the first time ever in my lecturer's notes, and I couldn't find it anywhere until they recommended a book. Yeah, but yeah, I'm sure it's out there somewhere, but very little undergraduate textbooks do second order degenerate perturbation. It's yeah, it's a pain. Yeah.
Yeah. Yeah. Yeah. You have to include coupling with the continuum. I,
Mhm.
I wouldn't have thought that would be the that would be the solution, but somehow it is. Okay. And I said two textbooks. So the third textbook I would recommend would be I keep recommending quantum mechanics, but that's my
No, I
specialization.
mean
So
that's fine, right?
yeah.
That's
What was it? Uh, well, I used to really like this one, but I'm starting to fall out of favor with it. But it's good for an overview, I would say. It's Yeah. I would use this textbook in combination with a second one. So the first one I would say, if you want to learn quantum field theory, a good introduction is well, you need it with the solution manual because the homework problems are very hard. It's Schwartz,
oh,
Schwartz quantum theory.
Schwartz.
Yeah.
I don't have it here. I have it. I have this one right now. The Peskin and Schroeder.
Yeah, Peskin and Schroeder. Yeah.
But this one is not really easy to read at all, actually.
Okay.
I
Um,
I don't really like this one. No, I like it, but like it's goes too quickly, I think. Yeah. But the shorts
Uh,
one, I heard very good things about it. My friends,
yeah.
I think it's a very common book in North America. Yeah, a lot of people in Canada also, and Canada and the USA use shorts a lot. So,
Yeah, actually, I heard about this book from he's a physics communicator on YouTube. It's oh gosh, his name escapes me right now.
is it Dobson?
Yes, Andrew
Andrew
Dobson.
Dobson. Yeah,
Yes,
that's the
yeah,
one. Yeah,
yeah,
of
he
course.
likes that book.
Very,
Um,
very famous. Yeah.
yeah.
Yeah, yeah.
The other book I would recommend to use, I guess, in combination with Schwartz for more depth
Yeah.
would be Weinberg's book.
Oh, Quantum Theory of Fields, right? That's one.
Yeah,
Yeah, that's volume one, two, and three. That's a good one.
yeah, yeah.
I A lot of people use that one, and then I find the third volume quite hard to understand. So I'm currently reading the first volume, and then I'm skimming the second volume a little bit. But yeah, the third volume is quite intense, I think. Goes into a
Yeah,
lot of
I
super, yeah, sorry. No,
no,
continue.
I was
Sorry.
just gonna say that I encountered the first volume in my undergraduate, and I wasn't ready for that. So I want to come back to it now. I think it would be a good experience now. Yeah.
Yeah, I mean, Stephen, it's kind of sad that Stephen Weinberg passed away. He would be really, really, really nice to meet Stephen Weinberg. And when you mentioned Freeman Dyson as well. Yeah, yeah.
I think you asked in the in our messages.
Yeah.
You asked who's someone that doesn't have the Nobel Prize, but I think
That's
should.
that's what I was about to ask you. Yeah, that's what I was about to ask. So it was one of them Freeman Dyson, do you think? Or
Yeah,
someone?
Freeman Dyson, definitely.
Yeah,
He deserved a
interesting.
Nobel Prize.
Yeah. Actually, I don't know that many. Typically, you know the physicists from the Nobel Prize, but that's a really hard question to ask. This is one final question I want to ask you.
Okay.
So, all of our lifetime is finite. So, what is one scientific or mathematical discovery you would like to see in your lifetime? Or it can be
Oh,
theoretical, it can be experimental. Like in your lifetime, what would you want to see, or what maybe you would even discover? Like what would you like to see in your life?
yeah. Okay. So actually, even though I'm a theoretician, there is one of the primary reasons why I became a physicist. So this is here's a little bit about me. Actually,
Mm.
I didn't start as a physicist. I started as a musician.
Oh, what do you
Yeah,
play?
I play guitar actually.
Oh, okay.
Yeah, I play
Mm,
guitar and I sing. I
mm.
used to be in a band, but
Oh,
anyway, I didn't like. Long story short, I just didn't like the entertainment industry. So,
okay.
um, I some things happened. It's a long story, but
Yeah, they,
eventually,
yeah.
eventually I passed 25, and I was like, okay, well, I should come back to school and do. I've always liked physics. I just it was a big commitment for me in my
Mm,
early 20s.
mm, mm.
So yeah, yeah. Where was I going with this?
You said
Um,
you said oh, what got you into physics in the first place? So I asked you
yes,
what
that's right.
discovered. Yeah.
Um, I one of the motivating uh, factors for me coming back to physics was actually climate change.
Oh,
And I would like to see nuclear fusion work.
oh.
I actually so this might be yeah, so this might be a little bit of a hot take, but I think that actually nuclear fusion would be one of the biggest contributors to a solution to climate change.
Mhm,
Simply because if you had a nuclear energy source that could be set up anywhere and
mhm,
was safe and stable and clean, then basically that that would fix our energy issues.
mhm,
Maybe I mean the current iterations of fusion reactors have a lot of issues with them, and I understand that this is where a lot of the pushback comes from. But I get the sense basically. I know we're running out of time here, so I would probably just say that I get the sense that basically if we could make an iteration of a fusion device, a fusion reactor that is stable and um, and easy to run,
Mhm.
I think that this would be the solution that we're looking for. Yeah.
Interesting.
So yeah, that's what I would like to see in my lifetime.
It's a great one. I don't know, my personal one may be too difficult. I want to see whether the black hole information paradox will be resolved in
Oh,
my lifetime.
yeah,
That would be far too difficult. I think I'm being far too ambitious. I don't think I
yeah,
don't know.
yeah. That's something that I think about a lot, actually. um, I I really like. There's a conflict between my practical side and my dreamer side, I guess, and I know that in order to actually verify whether a theory of quantum gravity is valid or not would require possibly a particle collider the size of the solar system. But at the same time, it's I'm a curious person by nature, and it's something that when I see a problem, like I, I don't know if you've heard this term nerd scope.
Yeah.
Yeah.
I think
Yeah.
that the thing is when people who typically go into physics, they always think about working in quantum gravity because it's such a
Yeah.
grand field. But then you realize when you get older, sometimes it may not work out because the problem is so difficult and the the experimental verification is so difficult for these kinds of theories. The energies that we have currently is far too low. So yeah.
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 Um, I guess before we wrap up, actually, I have a
Mhm.
question for you.
Mhm.
So, what do you think of since we're on this topic, what do you think of the current approaches to quantum gravity? Which one do you have a favorite, or
It's a
what do you
really
think
good
of string
question.
theory? Yeah.
Not really. I mean, if I want to go mainstream, I obviously would go with the current, what everyone's going for with string theory. But I do see a lot of problems with those kinds of theories because people say the dimensions are not correct. You can always they always have these non-unique solutions with the Calabi-Yau manifold, so you have
Right.
a very large landscape of solutions. I'm on board with the critiques argument, yet I will also say I'm not smart enough to dispute the people who actually do string theory. But um, there's one theory that I came across that I think is quite interesting, which is Roger Penrose's twist-star theory. But
Oh
I
yeah.
still am not really, at least in that case, the dimensions are correct. We're capable of
Right. Yeah.
getting four dimensions of space. But then again, there are some issues as well. I, but if you ask me to pick a candidate theory, I'd probably go with the mainstream string theory.
Okay.
Yeah. Okay.
Yeah. Yeah.
Yeah.
There's a lot I have to say about that, but
What's your
until
opinion,
I
Andrew? What your opinion? I mean, you asked me, right? I'm just asking
yeah
you the
yeah
same. Yeah.
yeah I think well if I'm free to speculate, I would say that I think that the string theorists uh, kind of got got scared and jumped the gun. I think that there's an iteration of string theory that actually does match the universe
Hmm.
that we
Hmm.
have right now. It's just that if you look at it in a naive way, it doesn't look like the right theory.
Yeah.
And so, okay, well, if I may be so bold, I've gotten some pushback from this on this before, but never from someone who actually was familiar with string theory. So I would say that that there was a so if you've heard of you must have heard of bosonic string theory, right?
Yes. The one
Yeah,
with 26 dimensions, right?
26 dimensions.
Yes.
Yeah, that would seem like the one that would be least likely to match our universe.
Yes.
But actually, this is the one that I think does match our universe.
Really? Okay.
Yeah, and the reason has to do with so if you'd have to think about it from the perspective of someone who have you ever heard of what is it the Kaluza-Klein theory?
Yes.
Yeah.
Yes. The
Okay. So
five-dimensional compactification. Yes.
Right.
So yeah.
Well, if you look at the Kaluza-Klein theory, really what that is a model for electromagnetism.
Hmm.
And it does actually match the standard model if you turn off all of the other forces besides electromagnetism.
Hmm.
And what that extra loop dimension corresponds to is the U1 gauge group.
Hmm. Hmm.
And so what I would say actually is if you count up all of the dimensions of the gauge groups,
Hmm.
you will find that you have a 16-dimensional manifold in
Hmm.
the standard model.
Hmm. Hmm.
If you then add to that, just naively add to that the space of metric tensors,
Hmm.
which is a space of symmetric 4 by 4 tensors,
Hmm.
you get 10 dimensions
Hmm.
extra on top of the 16 that you already have. So
Hmm.
if you add those all up, you get 26.
I think that's a really interesting take. But haven't we demonstrated in 1995 that all these string theories are part of one large M theory, like one different energy limit of M theory. So that's why I don't know.
Ah,
It's a
yeah.
more general.
That's the part that I'm not smart enough to talk about.
Yeah, exactly. Yeah. Then that I think that's
Yeah,
what's the problem, right? Um,
yeah,
to get into this field requires so much knowledge in mathematics. Like it's
yeah,
not even, I think at that point you're not becoming a physicist anymore. Those people who do these kinds of work, borderline mathematicians,
yeah,
they're even improving theorems in mathematics using
yeah,
string theory. So yeah,
yeah,
I
yeah,
don't know. I think that's the area where I guess in some sense I don't want to. It's not that I don't want to touch. At least I'm not ready to touch when it comes to that. Yeah,
yeah, yeah.
yeah, yeah, yeah.
Um, hmm. Yeah, as far as if they're all different limits of the, I think that still makes sense. But
Yeah.
yeah, part of the issue there is still so I'm kind of in a naive way counting up all the dimensions, just saying, oh, that matches. But
Mhm.
but
I mean, that's what
yeah,
particle
there's still
physicists do as well. Like they
right.
count
Yeah,
out the number of generators of the group and they say, ah, that's the bosons of the generator. Yeah. Yeah. I mean, that's normal, I guess.
but what the issue still would be, even in that case, would be how do you actually compactify those dimensions? Like
Hmm.
what specific groups do you
Yeah,
relate them
yeah.
to? 'Cause yeah,
Hmm.
so yeah, that
The
doesn't get rid of
my
the landscape.
I guess the main issue is like as as a theoretician, this is always quite nice. Like, oh, it seems to solve everything. But then again, how if like again, you say your daydreamer side and your practical side, how do you actually put this to the test? That's the
Right.
tricky part, I think.
Yeah.
Yeah. I don't have any more questions. Do you have any more?
Uh, Let me see. I don't think I have any more questions for. Oh, well, yeah, I do have one question for you actually.
Mhm.
I Before we started the interview, I took a look at your YouTube channel,
Mhm.
and your description. You mentioned that you play music.
Yeah, yeah. Oh, okay, nice one.
Yeah.
Yeah.
So, what kind of music do you play?
Oh, that's a good one. I like to play a lot of rock and roll because I find I just think it's my take. I play my favorite band is Queen. A very typical.
Cool. Yeah.
Yeah, I mean, but recently I've been playing a lot of Clapton because
Okay.
Eric Clapton because I find his guitars a little bit I wouldn't say easy, but the blues part is quite nice and it's
Yeah.
typically when you know the 12 bar blues, it's you can play a lot of the songs already, so that's why
Okay.
I play a lot. So
Cool.
I can ask you the same thing. What do you used to play, or what do you currently play, or
Yeah.
what do you like to play?
Yeah. So I like to play a lot of different things. If I'm playing acoustic, I really like flamenco music. Um,
Oh, I see.
yeah. If I'm playing electric, I really like to play like thrash and
Oh, I
and
see.
speed metal and that kind of thing.
Oh,
Yeah.
like what do you mean by speed metal? Do you mean like something like Guns N' Roses or Dragon Force or what's it or is it Slipknot? Those kinds of.
Yeah. Actually, way back in the day, I had a YouTube channel and I recorded a kind of crappy cover of Dragon Force, but yeah,
Oh, okay.
Through the Fire and Flames. I mean, it was okay, but I didn't have see, I'm kind of self-taught, so I didn't.
Yeah.
I had a really sloppy technique.
I think Dragon Force. I think some of their songs are nice. I think in some cases they can, in lack of better words, they can be quite memey. Like they can,
Yeah,
I don't know, like they're so fast and they're so disorganized. It's a little bit. It's on the meme level. I don't know. It's
yeah,
people
yeah.
use it as memes. I don't know. I think it's, but I like their music in some cases. Yeah.
Yeah,
Yeah.
I was more into them when I was younger. These days, I'm far more into, well, I've always really liked Megadeth.
Oh,
Um,
Megadeth.
yeah,
Yeah,
yeah.
yeah.
I think even though there are more technical guitarists, Marty Friedman is probably my favorite. One of them that's coming pretty close, though, is I don't know if you've ever heard of Guthrie Govan.
No. So yeah, continue. Yeah.
You should look him up. He's a jazz rock guitarist.
Guthrie Gold. How do you spell Guthrie?
Yeah,
G.
Guthrie. I think with an IE,
Ah,
Guthie.
got it. Guthrie. Ah,
Yeah,
the guy with the really long hair.
yeah, yeah.
Yeah, I see. Yeah. Interesting.
He is something else.
Really?
If you've ever heard of, have you ever heard of Steve Vai?
Yes.
Yeah. So there was, just to give you an example, there was a video that I saw of him jamming with Steve Vai.
Mhm.
And Steve Vai does a thing, right, in his Steve Vai style,
Mhm.
and then Guthrie Govan listens to him and he goes, "Oh, you mean this?" And he plays the same thing that Steve Vai played, and then Guthrie Govan plays a different thing in Steve Vai's style that Steve Vai can't play, and then Steve Vai is like, "What is that?" And then he plays it again a little bit slower, and then Steve Vai learns the thing that. So basically, Guthrie Govan is the kind of guitar player that will play your style, play it better than you, and teach you how to play something new in your style.
That's
I've never seen anybody else do that.
that's crazy. I don't know.
Yeah, he's a really fascinating person. He he thinks of music as a language,
Mhm.
and if you hear him jam with other musicians, you can hear him playing sentences at the other musicians. It's really fascinating to see it. I just I don't think I could ever quite reach that level.
Yeah, yeah. I mean, these guys are legends for a reason, right?
Yeah.
I mean, for me, I listen to more mainstream guitarists, I would say. Like,
Okay.
I mean, Clapton is quite famous. I mean, those like,
Yeah.
there's also Eddie Van Halen. Those more
Oh yeah.
mainstream guitar. I mean, yeah.
Yeah.
I still can't do his what's it called, the harmonic tapping technique. So I have to
Oh
learn
yeah.
that. Yeah.
Yeah. It's
So, yeah.
Van
Okay.
Halen was an inspiration in my younger days.
Yeah.
He's um
He passed away recently, right?
did he?
I think so.
Oh, I didn't know
Let me
about
see.
that.
30. I think he passed away recently. Oh, no, not even recently. 4 years ago.
Oh wow. How did I
Yeah.
not hear about this?
Yeah. I don't
Oh
remember as
wait, no. Now I remember. Yeah.
yeah.
Yeah. I forgot about that. Wow.
I thought it was last year, so yeah. I don't know.
Hmm.
Yeah. These guys are really interesting. Like
Yeah.
I don't know, my kind of guitar kind of style that I like to listen to is more like bluesy and more I do listen to a metal once in a while, but not frequently. I guess the only time I would listen to it now is when I'm working out, like because
Oh,
it,
okay.
'cause
Yeah.
it gives you the motivation to run and stuff.
Yeah.
Yeah.
Yeah. Cool.
Yeah. Okay.
Um.
I guess
Okay.
yeah, it was really nice talking to you, man. We can
Yeah. You
talk
too.
more on text more as well, and then we can
Yeah.
if
Definitely.
next time we can have a chat if you're free. So yeah,
Okay.
just
Sure.
a general chat. Okay,
Great. Yeah.
we'll see
Yeah. This
you.
was really fun.